Hello, everyone. Good morning, good evening, good afternoon. In this first talk of today, we have the great pleasure to receive Professor Calogero Vetro from University of Palermo in Italy. Professor Calogero is Professore Associato, right, Professor?
Right, yes.
At the University of Palermo. And today he's going to talk about general double phase functionals, recent results and applications. So, Professor, thank you very much for accepting our invitation, and you have the word.
Okay, thank you. So, again, good afternoon, good evening, and good morning, everybody, and many thanks to the organizers for the invitation, and to Professor Sousa for the nice introduction. It's a great honor for me giving this talk today here. Okay, well, I go to introduce the aim of the talk. I want to speak about some recent results about the existence of a weak solution to special form of differential problems in the sense of Dirichlet equation, variational and semi-variational inequalities, and obstacle problems, so in the realm of inclusion, obtained in collaboration with Shenga Zheng and other colleagues from China. The common point of our investigation is the fact that the main operator is built over a notion of a double phase operator with logarithmic perturbation applied to the whole operator. The problem is posed in a domain omega over n and is investigated under the setting of p, q constant exponent linked each other and linked to the dimension of the space. This is the prototype I use in the talk, but in some of the works, for example, the last one in the list, we also covered the case of the variable exponent. But since more or less the notation is the same and we have not the time to go deep into the proof, I prefer to use the standard setting. Also because the standard setting gives me the possibility to link directly our works to the nice work by Giuseppe Mingione, who substantially studied the features of the double phase operator, mainly in relation with the regularity of minima of the integral energy functional. I just briefly recall that the double phase functional is a prototype of phenomena where we have an energy density that may change its ellipticity and the growth condition. This is a special prototype of an isotropic functional as were introduced previously by Vasily Zhikov and Paolo Marcellini in the context of the calculus of variations and elasticity theory, with application in material science and fluid mechanics. But going back to the finding of Mingione, I like to recall that the name was coined just to identify the situation where if we go to distinguish in the set omega, the subset where the weight B is equal to 0, and the subset where B is different from 0, we know that in the first case, substantially the second term vanishes. And so clear both the integral functional and the operator reduced to the classical P-Laplacian. On the contrary, when we consider the set where B is different from 0, due to the relation among Q and P, so Q is bigger than P, and so substantially the second term is the prevalent one, and so the integral functional exhibit a Q growth. So substantially B acts as a switching coefficient between the two growth, and this is the motivation of the name. Anyway, about the regularity of minima, as I told before, and the strong connection of the existence of minima with the existence of solution of the corresponding Dirichlet question and others, I refer to a series of papers by Mingione and co-workers starting from the 2015. This is one of the most interesting papers, but there are many others. And this indicates, as I told you before, that the exponent P and Q are constant number, while for the counterpart, in the case of the variable exponent, I refer to the work by Ragusa and Takikawa. Of course, there are some differences among the two contexts, but at the right moment, we will give just some remarks to underline this aspect. Anyway, just to fix the attention, I chose to speak about this kind of problem. So this is an obstacle problem today in the sense of an inclusion. And of course, I will go to pose the problem in a bounded domain of Rn. But at the end of the talk, we approach also the case where we relax this hypothesis. So we consider also the case where omega is unbounded. Moreover, as you say here, of course, we have an additional restriction to the exponent in the sense that we have considered the critical Sobolev exponent P asterisk, and this is because the tools we use in developing our calculation are norm estimates and embedding type result. So a main part of the talk is devoted to characterize the properties of our double phase operator with logarithmic perturbation and in introducing the corresponding framework space that will be the Sobolev version of the Musiela-Coolidge space induced by the main operator. So we have to introduce now the other ingredient of the inclusion, the principal inclusion. But before this, I would like to spend just a few words about the obstacle problems. The story of obstacle problem is a long history, and indeed I like to refer to this paper in the 1889 by Stefan, where in this case, in the context of an homogeneous medium, he modeled the distribution of temperature in the case of a change of phase. And this usually is the typical case of a block of ice which is partially submerged in water. But I think that the work that mainly influenced the research after it is surely the monography by Jacques-Louis Lyon, where he proposed a detailed study of the equilibrium position of an elastic membrane lying over an obstacle. In particular, the crucial point is the equivalence, the establishment of the equivalence between the existence of the equilibrium position with the unique solution in the sense of the minimum of the Dirichlet energy functional associated to the problem. Of course, this monography is at the beginning of many other kind of investigation and then revived attention for boundary value problems. In particular, I also like to mention the non-local problem of the Kirchhoff type. So after this monography appeared many Kirchhoff versions of various problems and so on. Okay, so going back to our main problem, let's understand how we identify the multivalued function in our problem, starting from the definition of the obstacle. So basically, the obstacle is just an admissibility set. So we do not only need that the solution is in the right Musiela-Coolidge Sobolev space, but it has to overcome a constraint in the sense of a generic function. Well, starting from this set that is closed and convex, we go to identify its indicator function, and we get our first multivalued mapping as the subdifferential in the classical sense of convex analysis of the indicator function. This multifunction here is basically a maximal monotone operator. And I remark this point because substantially in obtaining, establishing the existence of solution, we go to work with basic multivalued analysis and also invoking the theory of operators of monotone type. So special occurrence in our thinking will be the notion of graph measurability and upper semi-continuity. This is because the real nonlinearity of our model, which are the functional capital F in the interior, a capital F in a part of the boundary, will be substantially modeled on the classical idea of a Cartesian function, of course, in the case of single-valued mapping. So this is what we aim to do. So the function capital F will be to graph measurable and upper semi-continuous function. but we will provide in some sense a construction of this function. And so we will pose some additional constraint, and we will deduce in the second part of the talk, we will construct this function over other multifunction. Why this? This is because apart from the basic theory, we use the theory of Clark and the recent painting in the book by Carl Lee. Basically, we go to model the hypothesis on the multifunction capital F by following this remark, which is substantially is an idea in the book of Clark, which is as follows. If we go to realize the multivalued mapping in such a way, we start from locally Lipschitz continuous function. We consider the Clark generalized derivative, directional derivative, and we get the subdifferential of this function. So substantially, we have to work with this set. Then, referring to the result of Clark, among other regularity of both the directional derivative and this subdifferential, we know that they are both upper semicontinuous. So we retrieve typically the hypothesis of upper semicontinuity that we need to impose over the function capital F. This leads to a special occurrence, and in this I go back to the book of Carl and Lee, because substantially, if I realize this is a subcase, if I realize the nonlinear function following this way, then as a special case of my obstacle problem, I can have this kind of variational and mu-variational inequality. So this is just a subcase, but it's a case of particular interest in application. But we will go back on this kind of problem at the end of the talk. So now we can really start by focusing on the principal operator and trying to understand what there is new in the consideration of this logarithmic operator, in the sense that the logarithmic perturbation is applied to the whole double phase operator. Well, first of all, the idea to work with a logarithmic functional. Also, this is of course not a new idea. I just collected two meaningful works at the beginning of the millennium by Fuchs, Seregin, and again Mingione, where substantially the logarithmic functionals were used to better cover the needs in plasticity theory. So the idea is to follow the deformation of a non-rigid material, and the logarithmic type of functional better answer to this situation, in the sense that we have to introduce some kind of smoothness in the description of the behavior of the material. Moreover, there are some aspects about the consideration of the logarithmic that Mingione discuss in his regularity theory. So in the way we go to realize the double phase behavior, but maybe we will say something about it later. Anyway, so this is the idea, to consider logarithmic functional. I repeat, introduce smoothness in the description of the phenomena. And now we see what already is known in the Liccia about in the context of P-Laplacian type operators. So surfing the Liccia, of course, we can find the P-Laplacian with the logarithmic perturbation, the P-Laplacian weighted with logarithmic perturbation, and this kind of operator, which is a combination of a P-Laplacian and a weighted P-Laplacian with logarithmic perturbation. So the logarithmic perturbation is applied only in one of the two operators. Now, if we follow the theory, in particular, we work with the context of Musiela-College space, each time we go from one step of this list to the next one, we see that the previous result, in the sense of well-posedness, norm result, convergence, embedding type result are confirmed. So each step confirms the similar result of the previous step, of course with some additional hypotheses, sometimes some tricks in the proof, and so on. So a basic idea in considering our operator is that we want to confirm the previous result. Maybe this is more or less trivial or predictable, but there is something more, in the sense that our idea, as I will say soon, is to show that this operator is a special form of Young function. In particular, is a generalized nice Young function. Well, we use the properties of Young function, and in particular, we go to pose an order relation, a way to compare nice Young function to originate our embedding type result. So in particular, we will go to revisit later a notion of weakness of one n function with respect to another Young function, which substantially means we will go to check an inequality. This inequality is proved to get the embedding of the space linked to each one of these operators in the others. So at the end of this first part of the talk, I will go to present a survey of the embedding of each operator into the others. Of course, it's clear that what I am saying for the constant exponent holds also for the variable exponent, and moreover, since we have introduced in the logarithmic this trivial parameter rho, it's clear that in the case rho is equal to 0, we cover also the unperturbed cases. So we consider also the double phase and the P Laplacian weighted or not in the classical sense. Moreover, we have another source of inspiration, not maybe a motivation, but an inspiration for our thinking, which arises from the field of applied mathematics. In particular, in the realm of approximation theory and in dealing with the method of expansion series, that is to construct the evolution of certain phenomena, we go to expand not the original operator linked to the phenomena, but its logarithmic perturbation. So our idea was to provide the logarithmic perturbation of the double phase operator and its framework to apply this kind of expansion series methods. I want to say, and I close this parenthesis, that this is pertinent to the case of the double phase operator, because the double phase operator itself has application in data analysis, because it is a prototype in image processing, so in problem of noising and denoising and filtering and so on. So it's pertinent, and maybe this kind of logarithmic perturbation could have some application, natural application in such a direction. Okay. After this, we have to start our technical mathematical analysis of the operators. So I go back again to the pioneering work by Zikov and Marcellini, and the crucial point is to understand what kind of growth is expected for the double phase operator and the double phase integral functional. According to the thinking of Marcellini and Zikov, substantially we go to distinguish in the Liccia between two kinds of growth, balanced growth and unbalanced growth. Balanced growth substantially means that I go to put a positivity restriction to the values of the weight, that is apart from a null measure set, B is always positive. In such a case, we have not the change of phase I have mentioned at the beginning, referring to the name of double phase, because the growth of the operator is between two same power growth, so it's in a strip. Of course, sorry, I have not precised this, but it's clear that I refer the growth to the double phase without the logarithmic perturbation because it's the same. I conclude saying that in the case of balanced growth, maybe it's not proper to speak about double phase because the behavior is more similar like the classical PQ equation, so the case where B is identically equal to 1. Differently, in the case of unbalanced growth, we relax the hypothesis on the positivity of B, and we retrieve the growth we have mentioned at the beginning. So there is the real change of phase between a P power and a potential Q power. Well, the two situations have to be studied in two different contexts. In the case of the balanced growth, we have to refer to the classical Lebesgue and Sobolev space with constant exponent And this is a prototype for depicting the behavior of composition of materials with different hardening exponent. And in the other case, in the case of variable exponent, we have the same formalism, but we cover the case of I told before, fluid mechanics, in particular electrorheological fluids, so fluids that change their viscosity in presence of an electromagnetic field that generates an orientation of particles. As usual, W0 is the Dirichlet version of the Sobolev spaces. So I told before, the formalism is the same, but every one of us know that there are crucial differences among the two settings, because we know, for example, that the Lebesgue space with variable exponent are not invariant with respect to translation, as in the case of the constant exponent. And we have also difference, and this is our key point in our dissertation, is a point related to the density of smooth function. And so we will put our tricks to cover these difficulties. Anyway, for more details and information on this theory, I refer to the classical result by Rakosnik and colleagues, Serin and Meyers, and of course the nice monography by Professor Radulescu and Repos. I want just to conclude about the question related to the invariance. For example, it creates also difficulties when we try to apply some methods like the Brezin-Nirenberg methods to construct the solution into a ball and then obtain by translation the solution in the whole space. Of course, if we have not the invariance to translation, we cannot apply this kind of methods. Okay. Differently, and this is the realm of our interest, in the case of unbalanced growth, we have to work in the general context of Musial-Coolidge space. So, trivially, the Coolidge space is linked to a Young function, so a negative convex function which vanishes at 0. When we go the Musial-Coolidge space, we substantially go to generalize the Young function in the sense that we consider the function of two variables, assuming the measurability with respect to the first one. And of course, this theory is strongly linked to the work of the Polish mathematician Władysław Orlich and Julian Musielak. But in this talk, I permit to follow the most modern notation, in some sense, Ariueto and Asto, because I think this notation is more easy to follow because it's conied over the notation of Lebesgue and Sobolev spaces with variable exponent. So I think it's more familiar to us. Okay. So we have to develop our finding, but before I want to underline that the research on Musial-Coolidge Sobolev space is actual. So we will develop our finding by using the classical result, which in such direction are the result by Liu and I, where substantially we find the investigation related to the definition of the norm, the introduction of the norm in the Musial-Coolidge space, the strong relation of the norm, which is in the sense of the Luxembourg norm with the modular, and so we have some kind of convergence and boundness result. I also like to mention the work by Collason and Squasina, mainly related to the establishment of the embedding type result. So in our investigation with Zheng and Zheng, we follow this line. And so now I will go to propose the similar result. But I want also mention this recent book by Juvarda and colleagues, where are shown some application of the Musial-Coolidge spaces, in some sense following the direction depicted by Jacques-Louis Lyon in his monography. But I want also cheat this nice recent paper by Chunky and Gening, where there is a very good discussion about Sobolev embedding in Musial-Coolidge spaces with some result about the optimality of the embedding and many other remarks. So following this way, I want to show that our double phase operator with logarithmic perturbation is a weak phi function first and a generalized and nice Young function later. Of course, we have not the time to discuss step by step all the result. I put the attention only on some crucial result, mainly related to the problem of obtaining the proper embedding type result. So the starting point is the definition of weak phi function, and in the definition of weak phi function, of course, I have to collect the properties. I point out the attention only on the hypothesis, so the items I will go to revise later. So it's clear that we assume the measurability with respect to the first variable, but our investigation is focused on the behavior with respect to the second variable. So I underline the fact that we need some kind of monotonicity behavior directly on the function, but also in the sense of almost increasing with respect to the quotient of the function itself over T. So this is a monotonicity type properties of, if you prefer, a Lipschitzian type condition. We also have to point out, and we will return also on the item Q, the behavior of the function at 0 and at plus infinity. So I have to vanish at 0 and blow up at plus infinity. Well, this is the basic setting as it's originated by the work by Musielak and Orlich, but in particular in their dissertation, Arriueto and Asso go to revisit, and this is what I do now, this kind of hypothesis. That is, they introduce two kind of additional hypotheses, which are named almost increasing and almost decreasing properties, where the monotonic behavior is shown with respect not at the quotient of the linear function, but the power p. Okay, of course, I have used two different exponents. There is a trivial motivation that will be clear in 1 minute. But I want to point out that these two hypotheses introduced by Arriueto and Asso are equivalent version of two previously introduced hypotheses. I start from the last one, the doubling, because I think this is the more celebrating hypothesis, also because it's largely used when we go to pose the similar theory in the context of metric measure spaces. And however, the meaning of these two hypotheses is that I go to characterize the behavior of my weak phi function with respect to its second variable by introducing properly some coefficient. So a main part in establishing this condition is in establishing the dependence of the coefficient. Well, to do this, now substantially have to understand what is the meaning of this hypothesis. Well, the meaning of this hypothesis is that we want to avoid too fast growth, so, as in the case of this kind of exponential function, but at the same time too slow growth, as in the case of the logarithmic perturbation of the linear function. Well, in our finding, we are able to prove that the double phase operator with logarithmic perturbation fulfills both the condition with an exponent, which in the case of the fast growth depend only on the big exponent q. In the case of the slow growth, depend only on the low exponent p. After this, we have to put some consideration about the density of smooth function, and in this sense, we have to carry out a proper analysis into a ball of radius or appropriate radius, and there we consider not directly our function phi, but its left continuous inverse in the sense of this infimum, and we show that it fulfills this kind of properties, A0 and A1. Properties, and in the book of Arriueto and Asso, there are other properties, A1 prime, A2, A3, A4, but just focus on this. The first one gives us a boundedness condition. So in some sense, it's used to establish the continuity of this embedding. The second property, instead, is a way to control the oscillation of the function with respect to the first variable. I have just a curiosity, I have highlighted in red, that this hypothesis is referred in the Licht continuity condition, but if we look at it, there is nothing about the continuity in this condition. This is just a similarity in the notation and the name of the properties with some kind of special situation in Lebesgue Sobolev space with variable exponent. Anyway, I have to go a bit more fast. We are able to prove this kind of properties under a bit revised condition on the exponent. Now we have to link PQ to the dimension of the space using a coefficient alpha, which is the Eulerian coefficient of the space where we have to put B. These conditions are not new because it's the set of conditions that the same Mingione studied and proposed as the set which ensures the maximal regularity of minima. So it's a middle set of hypotheses. Well, next step is to prove that our function is also an n function, which means I go to revisit the condition, I go back on the streams, not for the function, but for the function quotient t. Also in this case, I am able to show that these conditions are fulfilled. Well, now I have all the well-posedness of my function, so I can go to introduce in the classical sense, so I go fast, the Musiala-Colich space, so space of measurable function with this kind of condition of boundedness of the integral function. I introduce the Luxemburg norm, and I can go to prove basically that the space is complete, it's a Banach space. I can put the order inequality in the similar form like as in the Sobolev space with variable exponent, that I have my first result about the density of smooth function in the space. Of course, I can go to establish the classical result, which link the modular to the norm with the proper exponent, and the convergence of the norm linked to the convergence of the modular. Classical theory. Now I go to the situation of the Sobolev version of the space, so I have to include in the definition of the space the modular function. I introduce the proper norm with the component for the solution and component for the gradient. And again, I show that this is a reflexive Banach space. Now, finally, I go just a remark. I go to consider together or the occurrence of P Laplacian with logarithmic perturbation I have mentioned at the beginning, and I start my comparison analysis. So first I show trivially in item 1 and 3 some kind of relation. I am also able to develop some kind of estimate using the characteristic function. But what is important is that I can go to revisit these operators in the sense of weakness I have mentioned before. So I have to prove the existence of this inequality. By calculation, we show that the relation among the various operators are the one reported at the top of the slide. Now I can go to identify the Lebesgue Sobolev space to each one of all the space, and formally I obtain all these embedding type result. As usual, one arrow means continuous embedding, two arrow means that the embedding is also compact. Again, I can also obtain additional embedding, and I can also pose a Poincare inequality, which gives me the possibility to establish an equivalence condition between the previous norm in rand and this new norm, which simplifies the calculation. So this is the classical thing we are habituated to follow, starting from Lebesgue Sobolev space with constant exponent. Okay, so concluded the first step, I go fast to obtain the existence of a solution to our main problem. I told you that we want a weak solution, so I go to introduce the definition of weak solution, where the main point that we have to solve is to determine the good exponent and to select properly the selection mapping of our multivalued function. So this is the definition, and I have to work. The idea is to obtain this kind of result, which says that under the appropriate hypothesis on the multivalued mapping F, and adding an hypothesis of coercivity for element of the obstacle with prescribed norm, I am able to obtain the existence of one solution at least. The key of the proof is in establishing that this operator, so combination of principal operator and multivalued mapping, is bounded at the pseudo-monotone. Okay, first I examine the integral functional linked to the operator capital A. I show that this is C1, got us the Gateau derivative, and this trivially a maximal monotone operator in the classical sense. So I go to combine basically the S plus property and the coercivity type condition. And then I have to introduce the hypothesis. So the hypotheses are this one, where I have graph measurability and upper semi-continuity that I have mentioned at the beginning, and then I have to put a condition on the growth of, so it's a limitation on the supremum of the selection of a proper multivalued mapping. So I have to construct this theory, and so what I do is to introduce and combine the proper operator. I have to introduce the embedding operator, the trace operator, and the adjoint operator. Roughly speaking, I have to construct the mapping capital F as a composition of proper mapping, just to show that I can select the selection mapping in the right space as prescribed by the definition of weak solution here. Okay, so by manipulation and calculation, combining the hypotheses, I substantially know that my set of selection are non-empty. So I can operate in the classical sense and get this kind of result. So first show that I am in the right space, and then I show that both the multivalued operators are pseudo-monotone operators. This result is true for every closed and convex set P in the Sobolev Musilac space. Of course, all set capital K, the obstacle problem, is a subset of this situation. So this gives me the possibility to apply a surjectivity theorem as we can find in the work by Lee. Substantially, it says that if I am able to sum a maximal monotone operator, and this is the principal operator, and a pseudo-monotone operator, and this is the sum of the multifunction, if I have a coercivity condition, in our case, of course, capital L is equal to 0, then I have that the operator, the sum of the two operators is surjective. So substantially, in our first result, I go to rephrase the surjectivity theorem present in the work by Lee. I can proceed differently in the sense that instead of imposing the coercivity condition, I can obtain the proof of the coercivity as a byproduct. In such a case, I can go to implement another topological approach different, which is the method of sub and super solution, as usual. Of course, this method requires that I have to impose the existence of sub-solution and super-solution, which formally are similar to the definition of weak solution, but in few words are just a lower bound and an upper bound. So I have to restrict the hypothesis, adding this hypothesis on the existence of sub-solution and super-solution. On the other side, this gives me the possibility to impose the growth condition not for every values, but just in the interval. So in this time, combining again coercivity, hypothesis, S plus properties, and also some kind of truncation and cutoff function, I can go to prove the existence by using the classical element. Of course, I can do more in the sense that I can go to obtain the similar result discussing a finite number of sub and super solution. This is a way because in the idea of applied mathematics, so in approximation theory, I can go to approximate, restrict the interval step by step, and this can be interesting, I say, for the side of the application. But these more or less are the kind of result we can expect. We can also work more on the properties of the solution set, but I have 2 minutes and I want to provide 2 final remarks. So this more or less is all standard theory. So I jump again from a typical example I could use, and I want to provide just my conclusive remark about what change in the case where the exponents are variable and not constant. Well, despite the notation, we all know the notation, the main difference is that to get the similar result, in particular to get the density result and so the compactness of the embedding, we have to impose a log order type continuity condition on the exponent, and this gives us the possibility to conclude the hypothesis A0 and A1, if you remember the weight condition, and the one which is the control of the oscillation of the function. But I want also to give a remark about the fact of the unbounded domain. So if omega is not unbounded, I can obtain the similar result, but I have to impose a decay condition at plus infinity. And in particular, we have imposed a condition which is inspired by the standard logarithmic decay condition, but in an integral form. And this is the Neck-Vinda decay condition. In fact, so in the case that omega is an open set, I can go to prove to cover the question related to the density of smooth function, adding the condition of Neck-Vinda. And so also in the case of unbounded domain, we get the same situation. I conclude just saying that, of course, this is related only on the limitation from above, because in proving the other hypothesis, A0, A1, and the almost decreasing behavior, I do not need this kind of hypothesis. I think the time is right, so thank you for the kind attention.
Thank you very much, Professor Calogero. So if anyone has a question or comment, please just do it.
I have, Diego.
Yes, go ahead, Giovanni.
Let me see here. Calogero,
yes.
First of all, we from organizing committee are very happy to welcome you here in this seminar. Thank you very much for taking our request for a presentation, and thank you for this very nice talk. Now I have two questions.
My pleasure, thank you.
Is double phase problem with logarithm perturbation?
Yes.
Has comparison or maximum principle? In other words, does it work some sub-solution method for this class of problem?
Okay, sorry. You mean in the question about the existence, the solution of the existence problem, right?
Mm-hmm.
Or before in the definition? You mean here this to establish this result, or not?
I see this screen.
You see my screen, right?
Okay.
You see, is this point? You is at this point?
Very good. So, sub-solution method,
yes,
very well for this class of problem.
Yes, we work in the classical setting. So substantially, we give the same construction of the Minsky map, just to say. So we introduce the truncation just to identify the Minsky map, because in real, if you think, sorry, if I go to the hypothesis, one moment. Substantially, this kind of construction of the function f with the adjoint mapping, or it's more or less what we do when we identify the Minsky mapping in the case of the question.
Okay.
So the construction is the same, exactly the same, just with the fact that we introduce the selection mapping because they are in the multivariate context, but the approach is step by step, the one we follow usually in the question.
Okay.
I don't know if I have understood very well your question. Maybe it's not this.
Okay. And another question is, if the problem doesn't satisfy the delta 2 condition, how can we solve this problem without the delta 2 condition?
Okay. Without the doubling, we cannot, because we have the problem with in establishing the embedding. Okay, one moment. Because the problem, okay, the problem with the delta 2, it's this one, okay? Delta 2 give, in some sense, the limitation from above. Okay, usually when we work basically with regularity theory in general, the natural hypothesis is the one from below. So it's not always we put the condition from above, okay? This is true. So we could solve the problem, but we are not sure that in each situation we can control the growth. And so it's in our case, it's not sure we cannot get the embedding results we need.
Okay. Thank you, Calogero.
Okay, thanks.
Okay, is there any other question? I have one question.
Please.
Okay, you show some results for let's say stationary equation. Is there a theory or an extension of this kind of analysis to evolution PDEs? I mean, with
I am not competent on it, in the sense I am not expert, so I really don't know. I think something can be done in that direction, but really I am not expert, so I cannot provide a precise reply because I never tried. So I never tried, but maybe it's a good idea to see what can be done. Thank you.
Okay. Any other question or comment? So thank you very much, Professor Calogero.
Thanks a lot. I stop sharing the